it breaks down the two groups into a table, and they measured the cognitive load and motivation and retention, and also something called near transfer. So for cognitive load, it's predictable and expected that the worked example group had lower cognitive load. Of course, because they were given a worked example, they already know some of the steps to solving the problem. So they were consistently lower in cognitive load. Now, why is that important? If we look at some of the other results, for example, let's just go down to retention, and we look at the retention. I don't know what unit these numbers are in, but you can see that the worked example group had a 50% increased retention over the students that were just problem solving. So much better ability to remember how they solved that problem. And you can see they also scored better on near transfer. And I believe that means that when given similar problems, they are better able to solve those problems as well. The motivational scale has to do with how proud they were of completing the lesson or the challenge, and also how challenged they felt during that. As you would expect, the worked example group didn't feel that it was too challenging for them. And then for how proud they were of their achievement, the worked example group was also slightly more proud of what they did. So take that for what you will. But then if we go down to the essentially the educational implications, it's sort of giving, I guess, advice for maybe teachers or professors to recommend that when you are training or teaching someone who is just new to something, that you should give them worked examples, and then as they learn more and more, you can maybe peel back a few of the steps so that the worked example have less information and they have to do more problem solving over time. So you're doing this gradual increase to keep the cognitive load of the student manageable. Why do you need to do that? Because when you are cognitively overloaded, you cannot remember things. And especially if you are overloaded by a challenge and you get frustrated, you have even less chance to remember and get through that problem. So when we are doing things like going to LeetCode and jumping into a problem that we have never seen before, you are not cheating by looking at worked examples. The worked example will tell you how to solve it, but you will actually be better solidifying that knowledge in your brain and that pattern. Now, a worked example is very different from a completely finished and final solution. A worked example is the steps. It is not just the answer. If you just take the answers, you're not going to learn. But if you use a worked example, you're going to learn better than everyone else who doesn't. It just seems like a no-brainer for me. So when you go through here and you look at solutions, don't look at the solutions because they will have just a complete solution unless they've written it, their shared solution really well, which most of them don't do that. So instead what you do, you just go to an LLM and ask it to give you a worked example because they've all been trained on all of LeetCode and everything. So that's it. I will link the study in the description. Go have a read and good luck.
The year was 1936. Alan Turing asked a simple question: can machines think? Actually, no, that's not right. What he really asked was something way more boring. Can every mathematical problem be solved by an algorithm? Surprisingly, he proved the answer is no, but in the process, he accidentally invented the computer. 12 years later, in 1948, another legend shows up named Claude Shannon, and he reduced all human communication down to ones and zeros, casually inventing the bit like it was no big deal. One thing led to another, and now in 2026, we have 18-year-olds in hoodies typing import torch into Python files and cashing billion-dollar checks from venture capitalist boomers. But reaching this point has been underpinned by a century-long chain reaction of computer science papers written mostly by dead people much smarter than us. In today's video, we'll look at 10 of the most important scientific papers in the history of computer science and how they changed the world for better or worse. Our story begins nearly a century ago when mathematician David Hilbert asked the field's biggest flex of a question: is there a universal algorithm that can decide whether any mathematical statement is true? Or in other words, can we automate math itself? He called this the Entscheidungsproblem, which is German for decision problem. By 1936, Alan Turing comes around and gives a brutal answer to this question: no. But in order to prove it, he wrote this paper on computable numbers that had to define what an algorithm even is. So he imagined a hypothetical machine with an infinite tape, a read-write head, and a tiny table of rules. This Turing machine is the abstract blueprint for every computing device you've ever owned. Once created, he asked it to solve the halting problem. Can you write a program that looks at any other program and tells you if it'll finish running or loop forever? Turing proved that it's impossible for a program like this to exist. It simply leads to a logical contradiction, which means math has problems that no algorithm can solve. That's annoying, but 12 years later, a guy named Claude Shannon would ask his own annoying question: what is information as a thing you can measure? In his paper, A Mathematical Theory of Communication, he rips out the meaning from normal words entirely. I love you and the cat is on fire carry the same information if they're equally surprising, and he measures that surprise in a unit called the bit. He proved that all information could ultimately be boiled down to a stream of ones and zeros. But here's the crazy part. To estimate how much information was needed to transmit a message, he borrowed a word from thermodynamics nobody understands: entropy. To estimate entropy of English, Shannon made people guess the next letter in a sentence. When a letter is easy to guess, it has low entropy. When a letter is hard to guess, it has high entropy. But wait a minute, having humans guess the next token is exactly what AI does today, just on a much bigger scale. Shannon wasn't trying to build artificial intelligence, but he gave us the math for uncertainty, prediction, and compression, and accidentally wrote the spiritual ancestor to the loss function. And that's exactly why Anthropic named their AI model Claude. Then, 10 years later at Cornell, a psychologist, not a computer scientist, builds the first machine that actually learns. He gets inspired by the way neurons work in the brain, so he designs a thing called a perceptron that takes inputs, weighs them, and then adjusts those weights when it's wrong until it can classify patterns on its own. It's the building block for modern neural networks, and the hype is immediate and unhinged. The Navy funds it, and the New York Times reports that the computer will soon be conscious, but 11 years later, the hype would die out completely, thanks to two haters at MIT who published another paper with a completely different vibe. With basic math, they proved that a single layer perceptron can't even learn exclusive OR, which is just trivial logic that means this or that, but not both. This paper, or technically a book, was essentially a death certificate for AI at the time. Funding evaporated and deep neural networks entered their first AI winter, but there was a twist buried in the fine print. They actually figured out that stacking layers of perceptrons fixes everything. The only problem is that back then, nobody knew how to train a stack of perceptrons. It would take another 17 years to figure it out, but first we need to talk about times, clocks, and the ordering of events in a distributed system by Leslie Lamport, because neural networks are useless unless you can run them on a massive scale. This paper realized that separate computers with no shared clock can't really have a universal now time, and that's a big problem when you have multiple computers in a distributed system trying to do things in order. Well, he figured out a way to fix this with the happen before relation. You stop trusting the wall clock time and order events by causality instead. If A could have caused B, A comes first. From that, he builds logical clocks, which allow an unlimited number of machines to stay in agreement without ever looking at a real clock. Eventually, this paper would become the bedrock for every database, blockchain, and every massive AI training run, because you need thousands of GPUs that constantly stay in sync and agree on state without dissolving into chaos. That was a game changer, but 17 years after neural networks were left for dead, the three researchers, including the godfather Geoffrey Hinton, answered the question that everyone gave up on: how do you train a stack of layers? The answer is backpropagation. Run your data forward, measure how wrong the output is, and then push that error backward through every layer, using the chain rule from calculus to nudge each weight in the direction that's a little less wrong. Do that a few million times, and the network teaches itself. The crazy discovery, though, is that the middle hidden layers started inventing their own features, edges, shapes, and concepts that nobody programmed in. That exclusive OR problem that was impossible 17 years ago, it just became trivial. Backpropagation is still essential to neural networks today, but back then they sucked because we didn't have enough data or compute. Well, that was about to change in 1998 with the rise of the internet and this famous paper from Larry and Sergey about the anatomy of a large-scale web search engine. The paper describes the PageRank algorithm, where instead of ranking a web page by how often a word appears, it treats every link as a vote. And each vote is weighted by how trustworthy the voter is. They built a prototype in their dorm room, which eventually became a company called Google that you may have heard of. Most importantly, though, this algorithm helped assemble the largest structured pile of human text ever created. And that massive pile of text would eventually become the training data or feedstock for future AI models. We'd finally see this in action in 2012 with the legendary ImageNet paper, created by a dream team of Alex Krzyzewski, Ilya Sutskever, and Geoffrey Hinton. Remember when I said backpropagation needs data and compute? Well, finally, the stars aligned. The dataset is called ImageNet, and it's a monster dataset of millions of hand-labeled photos, while the compute is a couple of NVIDIA consumer-grade gaming GPUs. A grad student named Alex wires up a deep convolutional neural network, names it AlexNet, and trains it in his bedroom. Then he walks it into the annual ImageNet contest and humiliates everyone. This is a contest where AI models try to classify objects in an image, like hot dog or not hot dog, and while everyone was fighting over a fraction of a percent, AlexNet walked in and dropped the error rate by 10 points in a single year. And this freaked everyone out because it was suddenly clear that deep learning actually works. It just needs more data, more compute, and the right architecture. Luckily, we would get that architecture a few years later, thanks to Ashish Vaswani and Google. In the paper, attention is all you need. Around this time, large language models had a huge problem. They would start a sentence, and by the end, they would forget what they were even talking about. That's because they would read and predict tokens sequentially, one after the other. This paper fixed that by introducing a new architecture called the transformer that throws out sequential reading entirely. Instead, it lets every word look at every other word at once and decide what's relevant. Not only does this make large language models feel more intelligent, but transformers also scale better as well. Google made the big mistake of giving this architecture away for free, and now every AI lab uses it, and that's where you get the T in ChatGPT. Speaking of which, that brings us to a paper released by OpenAI in 2020. Language models are few-shot learners. Basically, OpenAI takes the transformer and then asks the dumbest question possible. What if we just make it enormous? Not 2 times bigger, but scale it to 175 billion parameters and feed it the entire internet as a dataset. They made a crazy bet that intelligence isn't some secret algorithm we're missing, but rather it simply emerges once you cross a threshold of scale. The end result was GPT-3, the model that ignited the current AI bubble that we're living through right now. What's crazy is that all of a sudden, this model could translate, summarize, and write code without ever being specifically told how to do these things. At such a large scale, it learned how to generalize these things on the fly. 2 years later, this paper would evolve into ChatGPT, which today is now a $1 trillion product. But when you think of named Claude Shannon, and he reduced all human communication
Ready for school? Try Milk Plus.
It was trying to do something really quite manual, where it was patching EC2 things. Let me see what it was doing exactly. Like, and gets lots of users. Bash commands. Configuring Raft node side, you just run kubeadm join helm of YAML the installation of Bezos for evil of having access to the operating system, and simply
So software engineering has been changing very fast, especially in the last few months. And I think we're at a time that we need this. So this is a very simple Golang abstract where we have our data inside of the server. So the files, this is a map of ID to the location of the file. And of course, if the server dies, the data is also going to be lost. Basically, this is a very simple solution, and of course you already know how to solve. Probably just add a database, but the idea here is not just adding a database, is that you are going to decouple the server that's going to be stateless to the database. There we go. So basically now we have our server and our database, and whenever we make requests, we're going to get the data from the database so that our users don't lose the data whenever they make a request and our server is down. So now we have data persistence, and our first problem is actually solved. So very simple, we're going to get there. It's going to become more interesting, I promise you. But it's also important to understand why do you want to add a database at all. So it's also important to understand these little details. And what happens as well when you want to scale? This is our second question, which is, if you actually scale this instance here with the data, what's going to happen is that you're going to have two servers, for example. So we're going to horizontal scale, we're going to get there. But if you want to have multiple instances, basically we're going to have duplicated data. And of course, this is not desirable. It will work because you're going to have still the data there, and a request comes to the second server. The data is still going to be there, right? So if you make a request to this one, but the problem it comes here when you have data synchronization. So if the user writes to this machine, the data is going to be written here, but the other one is not going to know. So this is another problem that we have to solve, and it is solved by having a decoupled instance right here. This means that we can actually scale our server, and the user, whatever instance he uses, it doesn't matter because we have one singular relational database. So a database that is going to hold the user tables, the file tables, so everything is going to be held here. And what we can learn from this is that this is the classic separation of concerns in software engineering, which is the server is concerned with serving the user, while the database is concerned with storing the data. This means that if the server dies or it's removed, the database is not concerned with that because it doesn't know about the server. The server knows about the database, but if the server or the database gets down, of course, this is different because if there's no database, there's no way to serve the user. But in some cases, the requests don't need to go to the database. So there's some decoupling here. This is kind of the key takeaway from this first lesson. So here is the concept: data coupled to the machine equals no scale and no resilience. Let's take things a bit further. So here is our simplistic architecture. Now, let's imagine the following. Our application is doing well. We're getting a lot of users. It's getting popular on the App Store, but we are getting complaints that our app is slow to respond. So basically the server is not handling all of these requests as it should. Of course, let's actually scale it. So we're going to scale to a second instance. Now, what happens here, and we have already seen this before, that we can scale independently our server. That is good, but there's a whole lot of problems when we add more than one server. We're starting to get into a distributed architecture per se, because we have multiple servers, and in this case, they don't need to talk to one another, but we need to have some way in the middle to know who is going to be the server. So imagine that most of the users are actually going to this one, and this one has a lot of free resources to use. The users are going to get a degraded experience because this server is not being about us. And we also have to have a piece in the middle here that is going to decide which server is going to be the one serving the user. So this is usually called a load balancer. Do we actually have here? Yep, we do. Awesome. So this is usually called a load balancer. And basically, let's put our architecture here. Let me actually move our servers and duplicate it. Now we have another piece in the middle that actually is responsible to just redirecting to a healthy machine. So whenever you hear a load balancer, it's just this piece in the middle that is going to redirect to a healthy machine, or in this case, it might use that nomenclature, or it might just redirect to kind of a round-robin algorithm. So what this means is it's an algorithm that is going to, on the load balancer, that if the user A comes in, it's going to redirect to server 1. If another user comes in again, we're going to redirect to the other one. So kind of sequentially alternating between the servers so that they both get the same traffic. But is the traffic actually the same? If user A actually uploads a file, so let's say that he's going to do, let's start kind of designing our API as well. If he starts uploading a file, whilst user B is just getting a file, so he's just consuming a file, right? So he's getting file 1, 2, 3. Is this actually the same traffic? Is this actually the same request amount? Of course not. This is going to be more storage expensive. This might be more CPU expensive. So there's here different experience.
How did I learn Rust? Let me tell you. The first thing I did was I read the Rust book. You should be able to get through this by just 1 to 2 hours a week, really. Any more than that, and you should be able to fly through this. You can probably cover several chapters in an hour. Just do a couple chapters at a time. By the end of this, you should feel relatively comfortable. And then after that, I would recommend that you go and do the Rustlings. Rustlings is a project on GitHub where it's full of snippets of code, and they have tests, and you have to fix the snippets of code so that the tests pass. So it's got all these exercises. You go through all these. And then the next thing I would do is probably go on, say, LeetCode or NeetCode. Let's say you go to NeetCode, and then you look at the roadmap, and you complete this triangle here, just that triangle. And then you could go to Exorcism, and you could do, say, one of the language tracks for Exorcism. And by this point, if you're a quarter way through this and you still kind of aren't sure about a project to do, then just keep going. It's a lot of work to do this. It's easier said than done. But let's say you get through this thing, you implement like 5 of these or 10 of these, then maybe you have a project idea. So you go do your project, and then maybe you could go on and look for a book, Zero to Production in Rust. This book will teach you Rust and back-end engineering in the same book. So you go through this, you apply yourself, you'll know back-end engineering, you'll know Rust, and then you really want to become a master. You go through Rust for Rustations. And then at the end of that, you could be a consultant. It's a lot of work that I just laid out for you.
This AI agent can create cinematic commercials from WhatsApp. AI agents are evolving insanely fast. But today, I'm going to show you something that honestly feels like the future. I connected her generation, and this entire commercial was generated from a simple WhatsApp conversation. Watch this. I send Hermes agent a message saying, create a cinematic commercial for the Omoda 5 driving through Johannesburg at night. Hermes downloads references, builds prompts, connects to Higgsfield, generates cinematic shots, and outputs an actual commercial. This is where AI agents are heading. Here's the full stack we're using. First, we have Hermes agent. Hermes acts like the brain. Then we connect Higgsfield through MCP. That gives Hermes cinematic video generation abilities. And finally, we connect everything to WhatsApp. So instead of sitting at your PC all day, you can literally control your AI creative studio from your phone. You can generate ads, generate cinematic scenes, create product commercials, build social media campaigns, create short films, even automate content creation pipelines. This is honestly one of the coolest AI workflows I've tested so far. First, we need Higgsfield connected to Hermes. Go to the Higgsfield CLI page, install the CLI, then authenticate your account. After that, install the Higgsfield skills into Hermes agent. Inside Hermes, you'll now see the Higgsfield skills loaded into your agent. This is where things become powerful. Hermes can now understand prompts, build workflows, and generate cinematic assets automatically. The final step is connecting WhatsApp. This allows you to message Hermes from your phone like a normal chat, which means your AI agent becomes accessible anywhere. For an in-depth tutorial on how to connect Hermes agent to WhatsApp,
capacity. Let's kick off. I don't want you waiting here for 25 more minutes before some arbitrary deadline. So, welcome. My name's Matt. I'm a teacher, and I suppose now I teach AI. We have a link up here, if you've not already been to this, which has the exercises for the stuff we're going to do today. This is going to be around 2 hours, so we might just sort of kick off 2 hours from now. Is that all right, Mike? Yeah, perfect. And the theory behind this talk, or at least the thesis under which I've been operating for the last kind of 6 months or so, is that we all think that AI is a new paradigm, right? AI is obviously changing a lot of things. You guys are obviously interested in this, and that's why you've come to this talk. And I feel that when we talk about AI being a new paradigm, we forget that actually software engineering fundamentals, the stuff that's really crucial to working with humans, also works super well with AI. And this is what my keynote is on. Tomorrow, really. I'm going to sort of be fleshing that out a lot more. And in this workshop, I'm hopefully going to be able to direct your attention to those things and hopefully show you that I'm right. But we'll see. Can I get a quick heads up first? How many of you guys have ever coded with AI? Raise your hand if you've ever coded with AI. Perfect. Okay. Keep your hand raised. Let's all share those armpits with the world. You don't need to worry about the code. You just... At this point now, I have used 25k tokens, and all of that, or loads of that stuff, is gold. I want to keep that around. I've got 25k great tokens there. And what I want to do is kind of summarize it in some kind of destination document. So this is
few months ago, I wrote a few sentences, about 4 sentences, that have turned out to be the most influential 4 sentences I've ever written. I packaged these 4 sentences up into the Grill Me skill, which is a skill that you can use to get the LLM to interview you relentlessly. It interviews you until you reach a shared understanding, walking down each branch of the design tree, resolving dependencies between decisions one by one. I know this skill is influential because every single day I receive about 5 messages of people saying they've tried it and they love it. This skill is an absolute game changer. What are your favorite skills? Grill Me is great. I'm working on a project, blah, blah, blah. The Grill Me skill asks me about ambiguities. Fantastic. Grill Me skill is goated. At first, I felt like it slowed me down with all the questions, but after using it a bit, I honestly think it might save time. You just one-shot everything after you've kind of gathered all the context. And you tested the skill called Grill Me and blah, 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 blah. It's wonderful, 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 wonderful. And after all that praise, you might think, well, you should probably stick with that skill, shouldn't you? That skill sounds pretty good. And it turns out I've actually built a better one. I'm never very happy when I'm resting on my laurels. I always feel like there's improvements to be made at every single part of my process. And now Grill Me has been replaced with a new skill. Let's open up a session so that I can explain a little bit more about where Grill Me goes wrong. I'm going to paste in a prompt that I've already added here. And this prompt is an idea for a new feature. I've just dictated this out, so you just sort of be spared the details of it. But essentially, I want to create a new entity in my database and a new entity that my app is going to deal with. Currently, this application deals in courses, deals in lessons, deals in videos, and sections and a few other things. And I want to add a concept of pitches. There's this kind of Mr. Beast style axiom where you should be thinking about the packaging for your video before you actually work out what's going in the video. And that's what a pitch is in this kind of setup. A pitch is really just the packaging for the video, the title, the description, how I'm going to frame it to people. And I create a bunch of these pitches and then pick the best ones and then turn those into videos. Now what you notice here is as I'm communicating with the agent, we're really focusing on language, right? We're really focusing on what is a pitch. I just had to communicate that to you so that you could follow along, and the agent will need to extract that information from me too. But there's also some extra jargon in here that the agent doesn't know about yet. For instance, I'm talking about standalone videos. What does a standalone video mean? Oh, of course, it means a video that's not connected to a lesson or a course. Now, of course, I know that. That's kind of like a term of art for using this whole setup, but the agent doesn't know that yet. It doesn't have any concept of what that is. So during the grilling session, it's going to have to ask me what a standalone video is or try to figure it out from the code. So as I used Grill Me more and more and more, I would start to notice these times where the agent was being really verbose, and I would have to remind it, no, there's already a term for that. And often, though, there wasn't a term, or I was kind of thinking about things in a very verbose way myself, and that wasn't being challenged by the agent. Or we would actually land on some really good shared language, and then that wasn't documented anywhere. So I started to feel dissatisfied with Grill Me because there was this piece missing from the puzzle, which is we were able to communicate about the code pretty effectively, but I would have to re-explain all of the non-obvious things about the code base and about the domain, the problem that we were solving, before we could do anything productive. So I started to think to myself, what is the thinnest layer of documentation I could use to just give the AI a bit more of a leg up? So I came up with this skill, the ubiquitous language skill. Ubiquitous language is an idea that comes from domain-driven design. This is the big blue book by Eric Evans that everyone goes on about. And what it does is it's essentially you're trying to create a document which is the language that's used by the codebase, that's used by developers, and that's used by domain experts. In other words, people that know about what you're building, but not how you're building it. All of those three groups should be using a shared language, because that means that a domain expert can go, okay, there's something wrong with this particular section of the app. The developer knows what they're talking about, and the code also reflects that. So what I would do is in the middle of a grilling session, when I noticed that we were needed to sharpen some language, I would use the ubiquitous language skill and call it with, ubiquitous language, and try to create a ubiquitous language.md as we were going. So I had grill me and I had ubiquitous language, and I was using them both at the same time. And I realized, wouldn't it be great if I just combined the two into a new skill? And here is that new skill. It is grill with docs. It has exactly the same text as grill me at the top here, but it has a couple of extra pieces. The first thing it has is the ability to look for a context.md file. And this context.md file will document all of the shared language that's inside that context. Now, context is like super overloaded, so I'm sort of uncomfortable, but maybe okay with it. It's essentially a bounded context in DDD is a part of the app in which you speak a shared language. So if you have a massive monorepo, you can have a context map here and have many different contexts inside. So that's how you would scale this to an enormous repo. But still, if you just have one pretty big repo where all the application is speaking the same language and the domain experts speak the same language, then you can just use a single context.md here. So it's instructed to look for this existing documentation to pull in this shared language. And then during the session, it's got some extra additions here to challenge language usage against the existing glossary, to sharpen fuzzy language, discuss concrete scenarios, cross-reference with code, and update it as you go. So this essentially helps you really sharpen your language as you're using the grill with docs skill, and this pays off as you go. I was asking some folks for feedback on this, and I got some really nice quotes here. So this guy used it for the whole of today. And at the start, it asked him to define a lot of terms. Some terms were hard to agree on and ones he would most definitely forget. But 4 or 5 sessions in, he started noticing that
was picking up the context during the grill session, and it magically aligned with the thoughts I had before the words came out of their brain. So that's what you get out of this. By documenting the non-obvious stuff, by agreeing on a shared language, you really can nail down and get a magical alignment between you and the AI, where you just have to use far fewer words to communicate what you mean. For instance, here's the one that I have in my repo here. We essentially just have a little description about what the what the repo is. Then we have a course and a course repo, and we have all of the entities inside here, course versions.
In this video, we're going to go over this Andrew Karpathy skills, which got over 100,000 stars on GitHub, and this skill is derived from this expose that Andrew Karpathy. In this video, we're going to go over this Andrew Karpathy skills, which got over 100,000 stars on GitHub, and this skill is derived from this expose that Andrew Karpathy has wrote. And if you don't know what Andrew Karpathy is, he is previously a director of AI at Tesla and a founding team at OpenAI. And currently, this expose has gone over 7 million views on X. And essentially, what this skill does is addressing the problems that Andrew Karpathy sees on X. And the first problem we see is the model here always make the wrong assumption. So it doesn't ask clarification question. When you give it a prompt, it just act on it. And the second problem that it sees is that a model here oftentimes overcomplicating things. Things can be run in 100 lines, often wrote in 1,000 lines. And oftentimes, large language model here making changes that they're not supposed to, without a clear understanding about the full side effects. So that's why in this video, we're going to take a look at what it is, how does it work, and how is it different compared to any other skills that we have used in the past. So with that being said, if you're interested, let's get into the video. Now, let's take a look at what this skill is trying to offer. So right here, you can see this skill here offers 4 principles that we can use in our project, which will basically wrote inside of our Claude MD file. So first principle here you can see is think before coding. Large language model here, like I said, makes wrong assumptions, doesn't clarify things, and by having this principle, it's going to force AI here to have to think before it's going to do the execution. And the second here is simplicity. Things that can be wrote in 100 lines of code never should be wrote like 500 or 1,000 lines of code, right? Never should be complicating things. And the success criteria here is that if a senior engineer says that this is overcomplicated, then we should definitely simplify. And that's exactly what this principle is trying to solve. And the third one here is surgical changes. So let's say we're making changes. Large language models should never touch code that are not related to the instruction that we provide. And that's essentially what this principle does. And the last one that we have is goal-driven executions. We need to have a clear goal on exactly how large language model here perform before it's going to do the executions. And it's similar to the first one, but we need to have a clear success criteria for the expected behavior on the end result. And that's the 4 principles that the skill is trying to introduce, and they all compacted down into a single Claude MD file that we can add into a project to make sure that large language model here never hallucinates when writing code. Now, to put this into practice, here you can see it tells you exactly how to install this. First of all, what we can do here is that we can install this in Claude plugins. Simply, we're just going to add the skill in our marketplace and install it. And the second option that we have is, let's say if you want to install this not globally, but in a project level, simply you can just do this curl command here and add this onto your new project. But if you have an existing project, you can simply just going to run this command right here, and simply it's going to write this rule onto your Claude MD file onto your existing project. Now, for my case here, I do have an existing project called bookzero.ai, where I help business here to manage receipts and transactions, all using AI. And what I want to do here is I want to install this onto this project and see how does it work. Now, in order to install this, all I had to do here is just going to copy this command. It's going to install this on an existing project. So here I'm just going to come over to a project terminal, open your terminal, and just going to paste that command here. And what this command does is going to modify my CloudMD file by simply adding those 4 rules onto there. So in this case, I'm going to click on enter, and you can see that it's going to modify my CloudMD file. So now if I were to open the git diff, and here you can see this is the changes that it has applied. And for most of you guys, you probably already have your CloudMD file or your existing project. And by installing it, it might have some contradiction or conflict with your existing rules. So what I highly recommend you to do is basically tell Claude Code to basically try to modify your CloudMD file once you paste those 4 principles to see if there's any contradictions, any conflicts, anything that's not following what you have in the MD file here doesn't really need that. It needs the instruction, a clear instruction on exactly what it needs to do. And we also have executions. So you can see skills that are being triggered whenever we trigger them, right? But CloudMD file is different, is that we enforce those rules inside of our CloudMD file, kind of like personality embedded into the model's brain. That every time when it do something, we don't have to mention it. It knows that because it's embedded into its personality, embedded into its soul, that is going to follow these 4 constraints every time we do something, when it asks to do anything, like maybe helping us to writing a blog post, or helping us to generate images, or helping us to writing code. It's going to embed that. It's going to do this exactly like we mentioned in our CloudMD file. So that's the clear difference between the two. Now, other than their types, let's talk about the functionalities, right? Because these 4 principles actually cover a lot of those things that we have mentioned previously on this channel for those skills that we have mentioned, like GStack, superpower, and GSD. How is it different, right? In terms of functionality. And you can see here that I asked AI on exactly the difference. And you can see here that rule number 2 and rule number 3 here has put it up by AI that is uniquely different compared to superpower and GStack, because none of them has mentioned anything about like adding extra stuff or staying in your lane, or they don't really mention about these things as like the constraints. They both teach how to work carefully, but they don't know how much like to do, right? Your guardrails here, which is, our CloudMD file here, fix that gap by combining all of them, right? Combining the 2. Not just showing them the constraints, but also giving them the path on exactly which skill to trigger. For example, each of the principles that Karpathy has mentioned like think before coding, like don't assume, like service the trade-off before writing code, we will give them the path on exactly what skill to trigger. For example, just a couple MD files is not going to cut it. We're going to let them to basically direct them to trigger the superpower skills. Like for example, the superpower brainstorming skill for adding new features. Or if it's like bug, error, or test error, like test failure, we're going to have them trigger the superpower system debugging skill. If it's a multi-step, like 3 files, we're just going to directly having to trigger the writing plan skill or the GSD planning phase skill. Basically try to execute it really fast, creating a to-do list and try to execute it, right? And for simplicity first, there's actually a bunch of skills for simplicity, like making code more simplified, like minimize the code that solves the problem, nothing speculative. So you can see before committing, polish. So whenever we try to commit things, okay, well, let's trigger the simplify skill and try to simplify everything. All right, so pretty much that's it for this video. And all right, so you can see that's pretty much it for this video. But with that being said, I'll see you in the next video. And honestly, don't even stop there. You can also include in GStack, like the auto plan skill, where you can be able to have different roles here to introduce for think before coding. The possibility here is endless, right? You can actually add a lot of things in here. For example, there's also surgical changes. You can also add like using different work trees for, breaking it into different environments. And there's also goal-driven executions, right? Making sure that we're setting a clear goal, right, for the success criteria. So implement a feature or bug fix. Okay, well, let's trigger the test-driven developments here. If it's like executing a written plan, well, let's do the executing plans, right? So there's actually a lot of skills that does that. For example, if we want to do the security review, there's also security review, there's also data audits, there's also QA. So we'll give them path to the skills that we have and making sure that not only following the constraints, but also calling the right skills to act on it, right? So you can see the possibility here is endless, and you can just pick the skill that you want and just add it into your Claude MD file, and Claude knows exactly what skill is going to trigger based on your preference. Okay, so pretty much that's it for this video, and honestly, I don't want to have my Claude MD file here to be too long, so I just wanted to keep it short, just keep some skills that I really like inside of a Claude MD file. Alright, so you can see that's exactly the Andrew Karpathy skills. And of course, if you're interested in learning more about Spectrum development frameworks, be sure to check out the playlist here inside of the description below, where I show you all the Spectrum development frameworks that I talk about on this channel on how you can be able to make your large language model here to be highly accurate when performing tasks on your project, right? So if you're interested for that, make sure to check it out in the link in the description below. If you're using large language model here to do research on your project, then you definitely need to check out this repository called Graphify. And this repository is inspired from this post that Andrew Karpathy wrote about the LM knowledge base. And for those who don't know who Andrew Karpathy is, he is the former director of AI at Tesla and a founding member of OpenAI. And essentially what he's saying here is that we can index our raw file here to make a large language model here to query information and also be able to maintain it. And this repository here, you can see it does exactly that. For example, let's say if you have a folder here contains code, documentations, you're simply just using the Graphify command skill and it's going to convert it into a knowledge graph. And once you convert that into a knowledge graph, this will reduce the large language model token usage by 70%. So instead of having AI agent here to reading the raw files or documentations every single time, Graphify here is going to index it for you and compiles your code base into a structured knowledge graph so that the large language model here is going to be much more faster, consumes less tokens, and much more accurate when finding information from your local folders because it's harder to create in the graph. And honestly, this is mostly for people who wants to read more than write, especially for doing research or exploring new code bases. And that's why in this video, we're going to explore this Graphify repository, and we're going to see how we can be able to install this onto our local machine, how we can be able to use it, like converting our raw files here into a knowledge graph. And later on, I'm going to show exactly how we can be able to add in informations, how we can query informations, how we can be able to add this to different large language model, extracting documentations, and so much more. So by the end of this video, your large language model here can have higher accuracy, lower token consumptions, and faster output. So with that being said, if that sounds interesting, let's get into the video. Alright, so to get started, first we're going to do here is to install the prerequisites. So right here you can see there's a couple of things we need. One is we need the Python onto your local machine, which is version 3.10 above. And simply just going to go to the python.org and it's going to install it onto your local machine. The other one here is we have is UV. And we can also use the PIPX, but I'm just going to use UV for now. So essentially what we can do here is that you can just copy the repository and pass it to Claude Code or Codex and try to have your AI agent here to install it on your behalf. But I'm just going to install this manually here. So you can see here, the first one we need to do is to install the Python and UV onto our Mac OS. So simply I'm just going to head over to a new terminal session, paste that command, and you can see it's going to install Python here and UV onto our local machine. Then the next thing we're going to do here, as you can see, we're going to use UV here to install the Graphify. Now UV is kind of like NPM for Python, right? So instead of having Node.js, which is using NPM, Python here is using UV. So now if I were to clear terminal and just going to do the install for Graphify, and now you can see it's going to install the Graphify NPM, or in this case the package, onto our local machine. And then what's going to happen here is that we're going to register the skills with our AI assistant by simply just going to run the Graphify install. This way, we're going to have our skills added onto our project, which you can see here. So we have our skill install, and also it's going to be living in this .cloud folder. And then we also have the Claude MD file, which wrote on how to use the skill. And of course, if you're using different platforms, by default, the installation here is going to install on Claude Code. But if you're using Codex, you can simply just going to do the platform Codex. And if you're using OpenCode, there's also a command for that, and OpenClaw, as well as the Hermes agents. So there's tons of options if you're using different AI agents framework, so you can just follow that as well. Okay, so once we have this installed, the next thing we're going to take a look at is the commands. So scroll all the way down, you can